All right, so I wanted to show you problem number 6. Number 6, you have a pulley right here, and the angle of the ramp is like a 35-degree angle, right? And I'm going to call this block that has a weight of 200 newtons, I'm going to call that block A, or mass A. And then I'm going to call this one mass B. I think that's what they call it in the problem. Okay? And then I'm going to do a force diagram for system A. I got weight going down. I got tension kind of going up at an angle. I got normal force perpendicular to that. Okay? So there's normal, weight. Oops, that's not weight. What am I doing? This is weight. And then this is tension. And this is a frictionless ramp, so I'm not worried about friction here. And I'll start drawing a series of reference lines. Okay? These reference lines are absolutely key because they give you a way to check your work. Alright? So, I think that's enough reference lines. Oh, I got one more here. So every vector, I'm just kind of connecting it down. Okay? And from my reference lines, I can see that this angle is 35 degrees. This angle is 35 degrees. And you'll see this familiar pattern where every other angle is actually 35 degrees. Okay? So that was my force diagram for system A. Okay? That's based on this system here. I can also do a force diagram for system B. Right? System B, I got weight of object B. I need to distinguish between weight of object A and weight of object B, which I'll do now. And then I'll draw tension up. Okay. Now, I guess I'll make a reference line here, and I'll say that, let's see here. Since we know the object's motionless, the system is motionless, then we know also that the velocity isn't changing in this case, so the acceleration is 0. Therefore, the forces need to add up to 0 as vectors, right? So if I make up positive, my tension is positive, and I add that with the weight of object B, which is in the opposite or negative direction. So I'm defining up as positive in my picture for system B. Okay? So tension plus negative weight of B has to add to 0, and that means that tension has to equal the weight of B in magnitude. Another way I could show that is I could do a vector sum diagram where the weight of object B going down and the tension, those vectors have to add to 0. And that shows that those vectors also have to have the same magnitude in order to add to 0. Now, from my diagram for system A, so this is system B's force diagram over here, system B. On the left is my force diagram for system A, right? Now I should do a vector sum diagram, right? So I'll have weight going down, okay? I'll have tension kind of like going in the direction of that rope, and then I'll have my normal kind of like coming up at an angle, kind of like that. Maybe now I'll extend my weight a little bit. And I know this is a right angle right there. This is my tension. This is my normal. And this is my weight of object A. It does help to make these vector sum diagrams, all your diagrams, it helps make them large. And then now I can start adding reference lines on my vector sum diagram. Again, these reference lines are absolutely critical. That's how you figure out which angle is your 35-degree angle, which allows you to solve the problem. And most people, by the way, mess that part up. They mess up the angle. It's just very common error that's made in physics. Now, if I look at my force diagram for system A, I can pretty clearly see that this angle here is 35 degrees. That means that this angle is also 35 degrees, just by logic. There's probably a rule in geometry you studied that teaches you that rule. And this one here has to be 55 degrees, right? So now I can actually figure out all my forces, right? So if I take the sine of 35 degrees, what I'll get is tension over the weight of object A, which I already know to be 200 newtons because it was given. So this was given in the problem. Okay, so now I actually know my tension. My tension is going to be the weight of object A sine 35 degrees. Now that's all I needed to solve the problem. Okay, because now I can just go over here, and since it's the same rope, right, I can say, all right, well, if it's the same rope, that means that the tension is the same everywhere, and that means that the weight of object A sine 35 degrees has to equal the weight of object B, right? And I'm going to put mg for the weight, and I'm going to respect that the mass of A times the gravity field of the Earth sine 35 degrees has to be equal to the mass of object B times g, right? And if I solve for the mass of object B, which is what we didn't know in the problem, I'll get mass of object A, g sine 35 degrees divided by g. And that's kind of cool because then g divides into itself to make 1. And when the dust settles, we have a solution for the mass of object B is going to be just the mass of object A sine 35 degrees. And I'll let you put the numbers in to figure that out. Now, what we can also solve for in this case is we can find normal force very easily. And even though the problem didn't ask for it, I'm going to go ahead and do that. So cosine 35 degrees is going to be, let's see, normal force over the weight of object A, right? So that means that normal force has to be the weight of object A times cosine of 35 degrees, right? So that means that normal force is going to be mass of object A, g, cosine 35 degrees. And I can easily find the mass of object A. The mass of object A is going to be its weight, because weight is equal to mg. So the mass of object A is going to be the weight of object A divided by g. That means it's 200 newtons divided by 10 newtons per kilogram. So that's going to be 20 kilograms, right? So this is going to be 20 kilograms is the mass of A times, anyway, it's going to be the weight of A. I didn't need to find the mass of A because we were given the mass of A times G, which is 200 newtons. So it's just 200 newtons cosine 35 degrees. Anyway, that's how you'd find the normal force. That's how you'd find the tension. That's how you'd find the mass of B, which is what you were looking for. A more interesting question is, how does this answer change if the angle were increased to 70 degrees? Well, if this angle here increases, what would happen? I think the sine of 0 degrees is 0, but the sine of 90 degrees is 1, right? So as the angle gets bigger, right? As this angle gets bigger, you would need more and more mass for mass of B to maintain static equilibrium. I can see that here because as that angle gets bigger, like to 70 degrees, 80, 90, at 90 degrees, the mass of A and B must be the same. I can see that because sine 90 degrees is 1, right? So actually this is easier to see it from. So the mass of B and the mass of A will actually equal one another at 90 degree angle. So anyway, I hope that helps. Hopefully you see this pattern of what's happening as this angle increases. And you can easily solve by putting 70 degrees in for instead of 35 degrees. And you will find that the mass of A is getting closer and closer to the mass of B, which is what would be required at a 90 degree angle. And that's what you would need to do. You would need to keep increasing the mass of B in order to keep this system in static equilibrium. Anyway, I hope that helps, and that's number 6, and I'll go ahead and solve 6 a different way on another screencast. Thanks for watching. Have a good day.